Hello. In the videos on classical probability and non-classical probability, we have learned about the humble Bernoulli random variable. In this video and the one on the binomial random variable, we will learn how we can construct new, more complex random variables by generating multiple independent Bernoulli random variable. In particular, by the end of this video, you should be able to explain what types of phenomena can be modelled using a geometric random variable, and explain the derivation for the geometric random variable. Before we get onto that, however, let's first briefly review what we have learned thus far about probability. One of the most important things that we have learned is the definition of the cumulative probability distribution function. We have learned that we define this function by requiring that if each event S in the sample space omega has a value x of S taken from the set of real numbers script r, then there exists a cumulative probability distribution function, F underscore X of small x, that maps each subset of omega that can be formed using this piece of set builder notation to a number from the set of real numbers between 0 and 1. This function has the following three properties. Its limit as you go to minus infinity is 0, its limit as you go to plus infinity is 1, and the function is right continuous. We have seen how this distribution works and this definition works in practice by considering the aforementioned Bernoulli random variable. Furthermore, we use the tossing of a fair coin as an example of an experiment whose outcome is given by a Bernoulli distributed random variable. To go through the coin example once more, we have seen that the sample space of outcomes for this particular experiment contains two possible events. Either the coin comes up tails, or the coin comes up heads. We have then done this business of giving each event in the sample space a value x of S, taken from the set of real numbers, by saying that tails is given the value 0, while heads is given the value 1. With this mapping in place, we were then able to construct a cumulative probability distribution function with relative ease. The final cumulative probability distribution function looked something like this, with discontinuities at x equals 0 and x equals 1, corresponding to the addition of new events to the sample space. The purpose of this video is to now consider what happens when we generate multiple Bernoulli random variables. In this video, we are going to consider a random variable that can be used to describe the following experiment. We toss a coin a number of times and we count the number of times, capital X, that we have to toss it before we observe a head. In the video on the binomial random variable, we introduced the notion of a tree diagram. At this stage in the video, I would thus like you to pause it and see if you can work out the answers to the questions shown here. First of all, draw a tree diagram that depicts how this business of tossing a coin until you get a head might pan out. Once you have done this, highlight the leaves that correspond to capital X equals 1 and capital X equals 2. Lastly, see if you can work out the probabilities for x equals 0, x equals 1, and x equals 2. Pause the video now and take a moment to work through this exercise. Hopefully you worked out the answers to the questions yourself. Let's now see if what you get is correct. Let's start by considering the probability of having the random variable X equal to 0. This is easy. Remember that x measures the number of times we have to toss the coin before getting a head. If we never toss the coin, we cannot get a head. The probability that x is 0 is thus equal to 0. Let's now turn to x equals 1. The first time we toss the coin, there are two possible outcomes. We can get a head, or we can get a tail. The geometric random variable, X, measures the number of times we have to toss the coin before we get a 1. To have x equals 1, we must therefore get a head on the first coin toss. The probability of success on this first trial is just p, and thus the probability that x equals 1 is just p. Let's finally now turn to x equals 2. Remember, x measures the number of times we had to toss the coin before getting ahead. To have x equals 2, we therefore have to get a tail on the first toss and a head on the second toss, as shown here. Remembering that our Bernoulli trials are independent and identical, and that we can calculate the probability that both of the independent random events A and B occur by multiplying the probability of A by the probability of B, we thus find that the probability that x equals 2 equals 1 minus p multiplied by p. By continuing in this vein, we can arrive at the following probability mass function for the geometric random variable. The geometric random variable can be used to model the probability of that the first success is during the kth Bernoulli trial that we perform. Now make sure that you can answer all the questions below on this random variable, and then see if you can do the programming exercises on the variable. Thank you for your attention.